Good afternoon. Thank you very much for inviting me, and I'm really feel honored and humbled to deliver my talk, which is related to climate and weather. Essentially, to understand how can we make the course resolution climate and weather models to work for local level decisions. So that's is the theme of this talk. Um, sorry. If you're talking about climate and weather modeling, it's one of the very complex modeling process. So here we are essentially talking about if you're talking about present day climate or weather model, we are running some models which solves more than 5,000 to 6,000 partial differential equations which are coupled with each other, and you need high performance computing facility to run them for longer term. It's very complex. It uses atmosphere, ocean, land, and of course biosphere. So all of them you need to consider together to run this model, and you have to consider each and every processes, and some of the processes which you don't know we have to parameterize. So that's the way we run the model. I'm not going into details of this model, but which I'd like to highlight is over the last 20 or 25 years, there has been a silent scientific revolution which was not really discussed in details. And this is the very significant improvement in early warning system. Many of us know about 1999 super cyclone which took place in Orissa, and that resulted, as per government records, 15,000 deaths. Of course, the real number was much more bigger because it just considers immediately after cyclone how many people died and so on. Now, after that, there has been significant improvement in terms of weather modeling, and the results we can see in 2020 super cyclone Amphan or similar kind of cyclones. When it happens over the east coast, the number of death or fatalities is around 100. So that's the way. It's a significant scientific revolution which not only improves the atmospheric physics, climate physics, and so on, but also it is actually saving life. So this is what is very important, but we have a long way to go. For example, when we are talking about, I'm now going towards little bit of weather because we all know that climate is changing and because of which extremes are increasing. These are all well-known facts. But one of the things what is very important is if extremes are increasing, can we develop a very good early warning system and a very good decision support system which is sector specific based on that to make our technology, to make our sectors really weather ready and climate smart. That's the idea. So now when we are talking about weather modeling, there are multiple challenges. One of the challenges, uncertainty. Typically, this is the way a model runs. You can see on the left side, these are initial conditions. So when you are running a weather model, you need very good initial conditions. Now, if you need very good initial conditions, what we get is that we get a lot of data from satellite. We get data from different kind of sensors all across the globe. Some of them are shareable, some of them are not. And then based on that, we run the model. We use multiple ensembles. And then when you go towards future in the sense for next day, next to next day, third day, fourth day, and so on, what happens? One started deviating from another, which is the typical nonlinear dynamic process. So that results into more uncertainty. So the question comes here. The first thing is that there is observational uncertainty. How to handle this observational uncertainty? How to get good observations even? Because there are many regions across the globe which are ungauged, which are not properly monitored. The second thing is that there are multi-source, multi-formatted observations. How to merge them together to something which model can understand. That is second challenge. And of course, third is observational resolution. This is one of the challenge. Now, second thing is that let's say with all of this, you are still producing some forecast. There is a lot of uncertainty. But when you are communicating this uncertainty to a sector, for example, a renewable energy company wants that what will be the weather condition tomorrow so that I can know that how much solar energy I have to produce. It's very difficult to really communicate this sort of uncertainty because that person would be interested in only single value, not really uncertain. So even if there is uncertainty, how to really translate it to decision. So that really is a major challenge. The second challenge is the resolution. So if you are talking about global model resolution, it's mostly whatever is available globally. They are 25 kilometer. Of course, now we have come up with Bharat forecast system, which is 6 kilometer resolution, which is known to be world's finest operational weather forecast system. But still, it has some problem. All these models have some problem to generate meaningful information at hyper local scale. What does it mean that? I asked ChatGPT to generate the left side figure. Of course, it generated quite nicely. Of course, there are certain problems which I'll also mention. So one of the thing is that, for example, if you're talking about a 25-kilometer resolution, it will generate some forecast. Now, what is needed is, let's say if you're managing urban flooding, you need hyperlocal information. For example, in 2005, we had in Mumbai, on 26 July, we had extreme rainfall. Santa Cruz reported 900 millimeter of rainfall in 24 hours. Colaba, just 20 kilometer away, that reported only 83 mm of rainfall. Urban regions have very significant spatial variations. So how to really capture them? Because that is what the municipal corporation will be interested. They have to deploy all the pumps in those regions to pump out the water. So there are challenges. So essentially, how to really communicate this information to a practicing engineer or an expert. Of course, if you look at this figure, ChatGPT created it nicely, but the problem is that it could not understand the geospatial grids, so it uses some vertical grids and so on. But still, it is conveying what exactly I want to say. Now, in 2023, there has been a significant revolution that took place in the weather science. So before that, I'd like to mention that one of the important challenge, or one of the significant challenges, when you are developing higher resolution models, you need a lot of computing time, and at the same time, to address uncertainty, you have to run it multiple times. So you need significant time, and for real-time weather modeling, it's very difficult because you have to generate the uncertain forecast within a very short time. So that's the challenge. And then Google DeepMind came up with this model, which came in Science and which also got Science cover magazine. So essentially, it was published in Science and also got Science cover magazine, where they said is that, look, we are using graph neural network, and with this graph neural network, we are able to produce 11 days forecast with insignificant computing time, given that model is already trained. And so for this, you don't have to spend time, and up to 11 days, you are able to produce the model output, which is of very similar performance as a numerical model, which takes multiple hours in high performance computing in HPC system. So that was a major revolution, and hence it got a Science magazine cover page. Immediately after it was published, then there has been a significant number of publications. Almost, every 6 months we get either one Nature paper or Science paper on application of AI in weather modeling, and it's actually moving very fast. For example, this one of them is from NVIDIA, the other one is from Microsoft, and so on. They keep on publishing multiple papers in Nature and Science where they are improving the weather modeling and climate modeling using AI and ML. And of course, for a weather model or climate modeler like us, it's very difficult to really catch the pace of machine learning. But we are trying to collaborate and try to understand in what way we can improve the system. So now coming back to what weather modelers really do. So when it comes to climate or weather modelers, there are multiple problems. So first thing is that climate and weather models, of course, they have uncertainty problem, they have resolution problem. The other problem is that they have bias. Bias means if you are considering observations and if you are considering model output, there is a some kind of a regular error, or you can say the systematic error, which is bias, and this is well known. And for correcting the bias, what climate modelers normally do is that they first interpolate at a very high resolution and then bias correct it with respect to observations. And while performing the bias correction, what they do, they try to make a quantile mapping. That means same quantile they used to map with the observations and try to get something. So essentially, this is a data science based approach. But one of the things we are a bit worried that if you do such kind of bias correction, that means forcefully forcing the model output to observations, there are problems which you may face. And this is what one of my student Bikram Chandal did. What he did is that he picked up some simple random number and performed very similar bias correction. And then he found, so essentially you can see that the top row, it talks about observations, then the coarse resolution climate model and completely random number. Then when he performed the bias correction, you can see E, it shows that with GCM you are getting very good match with observations because you are performing bias correction. But on random number of also if you are doing, you are getting very similar results. Of course, you can see that performance is very good, but there is a problem. The problem is that because of this data science approach, you are actually forgetting what was there, what was the original property of the data. That means you are spending a lot of computing time generating coarse resolution model output, but then applying bias correction and forgetting what the model has done, and then just replicating the observations, which was a major challenge. And it is there over India, US, so there are multiple case studies what he has found, and he found that it's a major problem. I'd like to mention this kind of bias correction approach even was used in IPCC reports. So then what we showed is that because of this, sometimes the climate signal is getting amplified. For example, this is, you can see observation and global climate model, they are giving very similar pattern, but when you are applying this kind of corrections, it is getting amplified, which is again shown even in the random number also. So then, of course we published it, and it was highlighted in Science magazine, mentioning that this is one of the major problem of this kind of approaches. Then of course we came up with some kind of a machine learning approach which is known as YNet, where we are trying to do is that we are using standard approach where coarse resolution to fine resolution, we are improving the image quality, we are considering at every time step the variable values are kind of image, and we are trying to improve it, but at the same time we are trying to use some kind of spatial information that affects the weather. For example, if there are mountains, we know there are orographic precipitation. On the windward side we have different kind of precipitation, in the leeward side different kind of precipitation, we try to improve that. And also, so now there are other challenges that the machine learning models do not understand physics. So how can we incorporate physics? For incorporating physics, what we did is that we added some of the moisture transport constraints, some constraints related to moisture transport into the model, so that it can take care of east-west asymmetry of Indian monsoon. And when we did that, so we made the machine learning model to understand a bit of physics and then simulate the results. And when we did that, what we have found is that the models, I am not going into details of this model output, but what we'd like to mention is that we have generated multiple outputs, which is uncertainty, which is ensemble. But what we have found is that these models are able to find out, able to produce physics as well as high resolution output. So idea here is that now it's a time to really merge physics based information into machine learning models to come up with more physics informed output. Now, there are certain applications which I will be talking about today. One of the application is related to agriculture. The second one would be on renewable energy, and third one would be on urban flooding. So I'll start with the agricultural applications. Since we are in Mumbai and we are quite close to Nasik, so we visited Nasik to talk to some of the vineyard farmers. So when we started talking to them, we realized most of these farmers in Nasik, they have soil moisture sensors. And based on soil moisture sensors, they decide that how much water you need to irrigate. So what they do is that they check the soil moisture sensor values, and based on that, for next few days, they use a bucket model. Without considering any weather forecast, they find out what is the deficit, they apply the water. Then we asked them that, why don't you use the weather forecast? They said that weather forecasts are uncertain and they are for district level, so we do not know how to really use them. Then we talked to them and we made them understand that when you are talking about weather forecast, let's say 3 to 7 days, you can have very good forecast. We of course developed some method, co-developed some method with them. But their major interest was, what will be my water arrangement after 2 weeks? After 2 weeks, how much water I need to arrange? This is one of the major questions which the farmers ask. And then it comes seasonal prediction and decadal predictions and so on. So then what we did, we developed this kind of high resolution model, and then we use some kind of a stochastic optimization, where what we tried to do is that given a forecast, what will be the rainfall scenarios that is possible, we generated multiple ensemble and then used it in a farm scale hydrological model with a probabilistic constraint that, with a certain probability I can say that, your root zone soil moisture will be less than certain, should be greater than certain values, and accordingly you optimize the water use. And when we did that, we co-developed this method, we found that 10 to 30% of the water saving straightaway is possible without any loss in water yield. Of course, it was patented, and after that there are follow-on publications and so on. But this is something we found, and then we found that this is not only working up for 3 to 7 days, even up to 12 to 14 days, 2 weeks in advance, you are able to tell the farmers more or less correctly that how much water is needed for their farms, which was very useful. But remember, these farmers have sensor at their location. So we are only adding the water layer, weather layer on it. But the real challenge is something different if you are considering our country. One of the thing is that most of the farmers cannot really afford soil moisture sensors because they are very, very costly. And low cost soil moisture sensors do not work more than 1 year. So that's a major challenge. The second challenge is if you do not have soil moisture measurements at farm level, then you have to rely on satellite. Now the major challenge is satellite footprints are quite coarser compared to farm. The third problem is satellite normally measures at the surface level, but you have to go to root zone level. So there are a lot of challenges. So one of our students, Adrija, she was trying to develop some kind of a machine learning approach where she was trying to group different kind of farms within a village into some cluster, and for that cluster she was trying to find out if at least one sensor is available. Then getting the relationship of satellite soil moisture and fine resolution soil moisture and applying it to other farms over that region. And it was working well. For Nasik, we are getting some good results, which was okay. But real challenge comes when we really go to a village where mostly the farmers cannot afford soil moisture sensor, and there is nothing available. So for those places, we found it really difficult, and there are further challenges as well. So I'll show you some of the challenge. This is specifically taken from Nasik. So we have picked up 4 farms. These 4 farms are within sort of 1 kilometer radius. So, and you can see, so these green lines are rainfall and blue lines are root zone soil moisture as measured by the sensors. So you can see here that during the non-monsoon time when irrigation is happening, they are quite different from each other. Some of them are changing very fast, that means irrigation frequency is very high, and some of them are not changing very fast. So essentially, over this region, if you develop a relationship between satellite soil moisture and local soil moisture sensor and applied it to neighboring region, it's not really work, it will not work, and it was actually not working. So the question here is that then can we really use some secondary variable to really understand the human behavior, and also it also depends on the socio-economic condition and so on. Can we take secondary information and incorporate in the model? This is something we are doing, and this I believe is one of the major challenge to really do a proper soil moisture mapping. In fact, I'd like to mention that for Western countries where the irrigation patterns are very similar, their soil moisture downscaling is quite easy, and you can see multiple papers. But if it comes to Indian condition, there is so much of variation. It's extremely challenging to really map soil moisture at farm scale. That's one of the major challenge. So then what we did is so you can see if you pick up, if you train a model and then apply it to another farm, it goes like this. The top row shows like this. So then what we did, we just added a single information that we are asking the farmer every day that have you irrigated, yes or no. If you add this information, it starts improving. So the idea here is that if you get this information, yes or no, then further add the information for how many years for how many hours you have made the pump on. So that's the information they can provide. They cannot exactly provide how much water. So if you can add this sort of information, probably will do much better. So that is something which we are working on. And of course, getting this information, one of our student has come up with a startup which is Jalvix, which is incubated at Sign, and then we are trying to make it more upscaled over village level and sub taluka level and so on. The other thing is urban flooding. Of course, when I'm coming from Mumbai, I have to talk about little bit about urban flooding, because Mumbai is a city which is badly affected by extreme rainfall and flooding. So one of the major challenge, as I was telling, that for Mumbai, hyperlocal rainfall information is very important, because the rainfall spatial variability is very high, and we can see if you are looking at 15-minute to 30 minutes rainfall, which are very important for urban flooding, because urban flooding really happens because of high intensity, low duration rainfall events. This kind of rainfall decorrelates at 5 kilometer resolution. So this is very important. So one of the good part of BMC is that they have set up huge number of stations, around 60 stations are there within the city. So we thought that can we really take the global model output and develop some kind of a hyperlocal model with some of the machine learning techniques. So we started working with CNN based approach. So we have started using very simple CNN. It was working quite well for all the days, but when it comes to extreme days, it was not working well, because extreme days are really rare, and when these days are rare, you cannot really get very good prediction for extreme days. Then one of our student, Pooja, what she did is that she used CNN, but then she did a transfer learning with hyperparameter tuning, specific tuning of some of the parameters for the extreme days with rare data, and then trying to find out how is it working. So you can see the left side is the original global forecast system output for different stations, and you can see that hit rate is very bad. That means how many times you are actually predicting correctly the extreme rainfall. Now if you are using CNN, it is improving, but for extremes it's not really doing very well. But when you are doing it with this kind of combined approach, you can see the model is performing quite well, with 80% of the events were successfully detected. And then we also found that the false alarm has reduced quite significantly. You can see very high false alarm was there in the global model, but when it comes to regional model, hyperlocal model, it's decreasing. So this is something, but still there are quite significant false alarms. Then the other thing is that we thought that we also have to do something in terms of crowdsourced flood data, because there is no open flood data that is available for Mumbai, and if we have to develop flood model, we need some data, and you cannot have sensors all across the city at all the junctions of the city to really understand what is the flood level. So what we did, we started using Twitter data. That time Twitter was free, so in 2022 we started collecting Twitter data, tried analyzing them, and then getting it verified with some volunteers which are from different NGOs, and trying to understand if it is working well and not. Then what we have found is that from crowdsourced information you can get very good information. For example, on a specific day, you can see the first one is elevation information. One of the peculiar thing of Mumbai is that you can see the red part, this is the low elevation region, and because of the orography, this region receives very high rainfall. This is low elevation region receiving very high rainfall, and major slum areas are also concentrated over this region. So that results into extremely vulnerable high risk region over that locations. And then when we looked at the Twitter information, we are finding that most of the tweets are saying that these are the regions which have more reportings of heavy flood. Volunteers are also giving very similar information, and then on that day we have checked the automatic weather station information, they are also matching. When all of them are matching, so we realize that this kind of crowdsourced information will have some information that can be used. Then what we did, with that we started developing a flood web portal, which is mumbaiflood.in, which is operational during June to September. This is all done by our students of climate studies. So what we did is that we have developed some kind of a rainfall forecast system which provides next 3 days forecast system at different grids. And also interestingly, BMC was very much interested, Beyond Mumbai Municipal Corporation, and their additional commissioner visited IIT Bombay. They wanted to use it. But what also they wanted to make sure that they are reading the forecast correctly. So what they did, they have created a WhatsApp group where our students and faculty will be there, and then BMC officials will be there. Every day will share the forecast. They will look at this portal as well as they will look at the forecast shared at WhatsApp, and they will discuss, and accordingly they will plan. For example, we had very high rainfall sometime in August, and the previous day we have reported this to BMC, and then BMC started asking that what will be the tide condition, etc. We explained everything, and then interestingly on 18th and 19th August we had extremely heavy rainfall. In fact, our forecast said that 19th August will have more rainfall than 18th. When 18th extreme rainfall were happening, BMC knew that on 19th there will be even heavier rainfall, and they prepared their pumps like that, specifically over some of the northwestern region, and that helped them. So, and also what we did is that Mumbai has multiple radar, so we have developed some nowcasting system where we can show that this portal is for citizen by citizen. So essentially citizens will provide crowdsourced information and will do modeling, and they can see that how the heavy rainfall band is moving. Accordingly they can decide, let's say someone has to go from IIT Bombay to Dadar, they can really see that next 2 hours they should visit, or they should maybe postpone the meeting in Dadar. So that sort of information can be provided. So, and this is something which we did. We got a lot of data through crowdsourcing. We asked people that when you are seeing any water logging, you just inform your height and your some qualitative water level. Then accordingly it will produce the water level. So this is one of the day where water levels are being produced from crowdsourced data, and this was available immediately to people so that people can, anybody can see what are the regions which are waterlogged, and accordingly they can make decisions. And I'd like to mention why short duration rainfall is important, because you can see within 1 hour on 19th August, the water level by one of our sensors, it increased 120 centimeter to 240 centimeter. So that's the way the water level has increased. In 1 hour, there was this increase, it doubled. So that sort of things happened, and also we provide such information at station level. So railway stations are very important because local trains are lifeline for Mumbai, and we provided the information that what are the stations which are under trouble. In fact, we also provided the flood waterlogging condition 1 day ahead so that BMC can work. As I said that the northwest part of Mumbai, we said that this region will be waterlogged. They put lot of pumps, and actually that region received very high rainfall on 19th August, but they could manage it. And that resulted, of course, a press conference by the additional commissioner of BMC saying that IITB forecast helped them, which resulted into a lot of media highlight. But one of the major thing is that this specific event was also highlighted in Science Magazine, where Science Magazine has specifically highlighted our efforts, and they said that how did it help the municipal corporation. The other work which we are working with, Grid India. So Grid India normally takes care of the energy scheduling and grid scheduling and so on. So what they need is, because renewable energy forecasting is very important because of intermittent weather or intermittent condition or irregular weather patterns, the renewable energy productions become intermittent, and they have to manage or schedule the grid. So what they need is that they need the forecast at different levels. For wind and solar, they need very short forecasting within few hours of forecasting. They need intraday forecasting within the day, how will it change, and everything has its different purpose. They need day ahead forecast for next 3 days, how will it happen, and then week ahead forecast, that means medium range forecast up to 10 days. So these are the different forecasts they really needed, and they want us to really develop their forecast system. So we started working with it. So first we started with nowcasting. So for nowcasting, if you need model output for next 2 hours, you cannot run a model. So what we did, we look at the satellite images from INSAT. So there are cloud data, there are cloud cover, there are water vapor and different visibility information. We took all this information and did a video prediction. And with this video prediction, we started getting the GHI values, which are essentially radiation values that results into the solar power. And when we did that, we found that these are essentially, you can see that on the right side, there are some curves. These are not specifically sinusoidal curves which you expect on a regular day for solar energy. There, some abnormal peaks are there. These are essentially because of the sudden cloud, sudden fog condition and so on. But this kind of nowcasting model can really predict this sort of things. Then what we did, then we use day ahead forecast. So day ahead forecast means how can you improve 1 day ahead forecast. So if you on the top plot, you can see these are the forecasts which are being generated by different operational models which are coarse resolution. But if you use machine learning, we have used machine learning. I am not going into details of the model, but when we use that, what we found is that we can significantly reduce this forecast. These are for entire western zone. In fact, last 2 days we had a detailed meeting with Grid India. Grid India officials came to us and we had a detailed meeting, and they are very happy. So they would like to start using the western zone results for their work. Then next one is, now let us say, so the question of course will come, if you have nowcasting, why do you need 1 day ahead forecast, or if you have 1 day ahead forecast, why do you need nowcasting? So I'll explain it like this. So you can see the black line, these are essentially model output. This is the coarse resolution model output. Now if you are seeing blue lines are 1 day ahead forecast. And also if you are looking at the brown line is essentially coming from MOSDAQ, which is you can consider as observed data. So brown lines are observed data, you have to match the observed data. Now black lines are coming from coarse resolution model, and if you try to improve the model at 1 day ahead, you can see the blue line. And you can see the first 2 days, because of sudden fog condition or something, there is a significant drop in the radiation and the model is unable to capture. but when we do every hour revision of the model output based on the satellite condition, do a video forecasting and do that, then we are finding that low condition is we are able to predict. You can see the red line is the updated forecast based on the satellite information. So we are downscaling the model, then taking satellite satellite video predictions, the video prediction based on satellite data, then updating the forecast and providing it. And this is the way we can really help those engineers who are actually scheduling the grid for a better energy management. And the third one is week ahead management. So why do you need week ahead management? Because let's say if some of the solar companies, companies are saying that they have to do some kind of a change of technology, or some problem are there, they have to replace some of the units. In that case, there will be some drop. They have to inform it to Grid India, and Grid India have to make arrangements. So for that, what Grid India wants is that, for example, 10 days ahead, if I know that over this region there is a possibility of significant drop in solar energy, then I'll ask that please don't do this kind of replacement things this week, do it next week, and so on. So that sort of plannings are needed, and for that purpose we need hyper local multiple day ahead forecast. And what we are finding is that for that sort of purpose we are able to really find that 7 day or 8 day advance, that when there are chances of low production of solar energy because of lower radiation. This is for during the monsoon time, where based on intra-seasonal oscillations. So there is a scientific thing in climate or weather which is called intra-seasonal oscillations, which is within season oscillations. We picked up that physics of intra-seasonal oscillation, using that in constant in machine learning models, and try to update, and we are finding it's working very well. So these sort of things we are now providing to Grid India. Now one of the things which I have not really touched is the climate, health and early warning. Of course, if you are talking about health and AI, there has been significant progress. But in our country, we still did not make much of progress in terms of early warning, taking climate and weather input for health prediction. Let us say for diarrhea prediction or prediction of dengue. And this thing is very important. And if you look at IPCC report, they said that over South Asia, diarrhea, dengue, these are the major disease which creates a lot of problem, and these are often driven by seasonal condition, inter-seasonal condition, and so on. I'd like to highlight that in the last November 2025, there was a Nature paper just focusing on Mumbai, and they said that because of Mumbai flooding and high tide, there are increased number of diarrhea and increased number of death which continued for 5 weeks. And this came in Nature paper. Of course, after that the Nature editor wanted me to write a small communication, what could be different solutions and so on, where we talked about early warning. This is the right side where I wrote this one. But this is something which is also the need of the hour. So I'm just finishing. So what I'd like to mention is that we know that there are different sectors. If we talk about health, infrastructure, energy, health and so on. So there are different agriculture, there are different sectors. What we have to make is that given the fact that climate change is affecting each and every sector because of increased number of extremes, because of changing patterns, what we have to do is that we have to make every sector weather ready and climate smart. And for that we have to go for high quality early warning system. And when we are talking about early warning system, it has to be high resolution, it has to be super fast, so that you can generate the forecast before the extreme takes place. And this is or you will get the time to make arrangements so that you can really mitigate the bad impacts of upcoming extreme events. So for that, the impact for the usefulness of AI is quite significant in the area of weather and climate. And we have seen that lot of papers, lot of patents, lot of newer technology, lot of new startups are coming in this area, and probably this is one of the area which will help our country to become weather ready and climate smart in a changed climatic conditions. So these are my students. Of course, over the last 15 to 17 years I have been working in IIT Bombay, and all these students of course contributed to this work. I just presented their work on their behalf. Thank you for your attention. Good afternoon.